All right. We'll start off with the last session of the Quantitative Tuesdays. And today we will talk about spurious regressions and why understanding these types of regressions is so important for multivariate time series. We'll look into what cointegrations are and how can we test for cointegration in different time series. And we look at vector error correction models, vector autoregression models, and finally, we'll also have a quick recap of the Granger causality test. All right, we'll get started right away. Today, we'll try to finish about 10-15 minutes earlier to have an introduction of what everyone else is doing with quantitative research methods in their doctoral research. So we'll leave some time for that, for the discussion. Let's start off with what we have been doing in this series. From the very first session, we looked at cross-sectional data. Then we looked at panel data and how we could use categorical dummy variables in our research. Then we looked at, in the last session, univariate time series, and we looked at what are the different characteristics of these time series. We looked at unit root testing, and why is it important to have stationary time series, and how can we test that our time series is stationary or white noise. Different time series variables such as daily Bitcoin prices or annual GDP of the UK since 1950 to 2020. What we did last time was we looked at a quarterly data set for one variable. But today we will look at multivariate time series. And when we examine multivariate time series, there's a very important concept which is related to spurious correlations, which we will look at briefly before we get started. So the issue with multivariate time series is that you might have different time series which grow together with time. So when you conduct a regression analysis onto them, they might show very strong correlations, but in effect, they might have no association with each other. And there are some strangely interesting examples and of different data sets that when you perform a regression analysis onto them, you will get statistical significance and p-values which are pretty much close to 0, and the end result of that would be, if you use these regressions and you form your in statistical inferences based on that, your results will not be reliable, and therefore in multivariate time series we have to take care of spurious regressions. So these are some of the examples. We have these two different time series data that show that deaths caused by people falling from staircases is extremely positively correlated with iPhone sales. So does that mean more iPhones mean more people dying from falling downstairs? And this means that the more money spent on admission to the spectator sports is strongly negatively correlated with per capita consumption of high fructose corn syrup. So does that mean if we go to watch sports, we will lose weight or we will consume less high fructose corn syrup? And another one is to increase auto sales, market trips to Universal Orlando. Is that a good idea based on this association? Whereas effectively, it might not have any relation. So the number of visitors to Orlando's Islands of Adventure is extremely strongly correlated with sales of new cars in the United States. These are some of the examples where when you conduct a regression analysis using these type of data, you will get extremely strong results, but they would carry no meaning. And that's what we would call spurious regressions. There's actually a very interesting book on it by Tyler Wiegand. And this book talks about different, interestingly funny spurious correlations. And I've taken 3 out of those just to have an idea of what this could turn out to be. For example, here we have per capita consumption of mozzarella cheese, and it's very strongly correlated with the number of civil engineering PhDs awarded. Then we have per capita consumption of chicken, and that also very strongly correlates with the total US crude oil imports. I mean, unless all the crude oil is used in frying chicken, which is not the case, this is a spurious regression. Then we have a number of people who drowned after falling out of a fishing boat. It very strongly correlates with, and the correlation is 95.24%. It very strongly correlates with marriage rates in Kentucky. And unless you assume that marriage is meant to be correlated with people falling out of a fishing boat, which some people might, this is also a spurious correlation. So how do we know if we have a spurious correlation or if the variables actually do have some sort of an association with each other? We conduct a cointegration test. So the idea of cointegration is that if we do have cointegration between two variables, then our regression results will not be spurious, but they would have some meaning to it. And the variables that we are studying would be associated with each other. For example, we might have these kind of co-integrations when we are comparing prices of crude oil and gasoline, maybe not, or when we are comparing exchange rates and inflation. But when we conduct a cointegration test, we can say that if two variables are cointegrated, they are correlated in the long run. So they will not drift apart. They will not drift significantly apart from each other in the long run. They are connected in a way. So when we have two non-stationary variables, such as these ones over here, and they're co-integrated, it's fair to assume that they won't drift too apart. But how do we get to know if we do have co-integration between two variables? There are a lot of different ways to find it out. We can have a look at one of the simplest ones is Engle-Granger co-integration test. The idea is that if we have two variables like these ones over here, and if they do have co-integration, then there is a possible beta or a coefficient if we are estimating y using the values of xt, two different time series, then we can possibly get a value of beta with which if we multiply beta by xt, and obviously it could occur with a constant, which might be the difference between these two lines at this point, for example. So when we conduct this regression, we can possibly get a value of beta by which when we multiply it with xt and add that constant, we will get yt. If that is the case, that these estimates can actually predict the value of yt, and the error term that we get from that regression is white noise, which means that the error term is basically a stationary series. Then we can say that we have co-integration between xt and yt. It's a simple test where we go on with the simple linear regression model. Then we estimate the values for the error term using these coefficients. What we are doing is we are using these, the constant coefficient and the coefficient for xt to predict the values for y. And the difference between the actual values for y and the predicted values for y would be the error. When we generate this error, we conduct a unit root test on this error. And we can extract these error terms, and we can see if the error term is white noise, which means that series is stationary. Then we can say that yt and xt are co-integrated. So all we have to do is conduct a Dickey-Fuller unit root test, and we compare it with a specific set of critical values, which are also provided by Engle and Granger. That's one of the ways in which you can find co-integration. But if you have endogenous variables like these ones, you have three different variables, A, B, C, which could be co-integrated with each other. And it might be that A can be explained by B and C, B can be explained by A and C can be explained by A and B. Then we have a system of equations. So the previous test cannot include the system of equations into the co-integration test altogether. But for that, we have something called the Johansen co-integration test. We're not going to go into a lot of detail of this, but just to mention that it's very useful where we have a system of equations like these, where we have multiple time series which are endogenous. Then we can use a different type of co-integration test. The idea is that if we do have co-integration, then we can estimate a model using a vector error correction model. This is also a type of regression where we have both long-term and short-term dynamics. So the idea is that if the error term from this linear combination, from this linear regression model is stationary, which means that if we have co-integration between x and y, then the OLS representation, then the OLS representation, which is this same linear model, would represent our long-term relationship, or we would say that in the long term, in the equilibrium, if xt is a certain value, then by plugging that into the equation, we can say that xt multiplied by whatever beta is plus alpha would give us the approximate value for yt. So they do have a long-term relationship. They don't have a long-term association with each other, where our equilibrium model will be estimated by this regression. But we can also have a vector error correction model, which tells us that even though we might have an equilibrium model or a long run model, it's very likely that that yt might have some short-term deviations. So yt might not be on the equilibrium point for most of it, but every now and then actual values for yt might be a bit far off the predicted equilibrium values of yt. But because we have co-integration and the long-term relationship, what happens is that if the actual values of yt go further from the equilibrium, we have an error correction term, which is the second part of this equation. And the error correction term is meant to bring the points back to the equilibrium. So let's say the reason why we have this as negative is that if the actual values of yt fall below the equilibrium, then by that amount of error, this term will bring it back to the equilibrium. So that is why it's called the error correction dynamics. What we have over here is that in an error correction model, if your dependent variable falls off the equilibrium line, then we have a mechanism within the equation which brings it, and on average, this whole part within the brackets on average will be 0, because we have just basically, the way we got this equation is rearranging our original regression model over here by taking the predicted values of the error term outside of the equation. We have on average yt minus alpha minus beta times xt will be 0. So on average, this whole term will be 0. So what we are just predicting is that the difference values for yt equal a certain constant plus a certain number of lags. So the same idea from the auto-regressive models in the last session. We have, so basically, deviations in yt depend on its own past deviations, but not only on its own past deviations. Deviations in yt also depend on the past deviations of xt. On the past and current deviations of xt. So we have a short-term model where short-term differences, short-term fluctuations in yt can be explained by very recent short-term fluctuations in the past period with one lag, or if it's daily data, then 2 days ago or 3 days ago. These just take care of lags. So sometimes if our model just has one lag, then we can get the summation sign out of the equation. It's just going to be a simple model with one lag. But what we have over here is for whatever the number of lags, the idea is that the short-term fluctuations in yt can be explained by the previous fluctuations in YT up to a certain lag, or up to a certain number of days or months, depending on how the data is structured. But not only its own previous values, its own previous fluctuations, but also the previous fluctuations in XT. However, when we do have these short-term fluctuations, we have an error correction term, which brings those fluctuations back to the equilibrium point, which is why this lambda term, which we estimate in a vector error correction model, is called the speed of adjustment. Provided that if this equals to 1, then an error in the past period will be immediately adjusted by its full amount, and in the next period we would have the equilibrium adjusted, the whole model adjusted for the equilibrium immediately. If it's equal to 0, then there is no error correction. So then we just have a simple vector autoregressive model. But the error correction dynamics can be used when we have co-integration. If we don't have co-integration, then we don't have a long-term model. Then we can only estimate the short-term model in first differences. What we have next, so this equation was for only difference YT. And what we can do exactly the same. So we have a vector of error correction models, hence also abbreviated by VECM. We have a vector of error correction models, this one for YT, and in a very similar way, the same for XT. When we estimate these, what if we have lambda 1, which is this, is statistically significant and it's between 0 and 1. It has to, for the model to be stable. But we have lambda 2 is 0. Then we can say that YT corresponds to disequilibrium, which means that if there are short-term fluctuations in YT, they will be corrected for because of the error correcting term being statistically significant. But we cannot say that for XT if lambda 2 is 0. The idea is that we don't have the error correcting term over here. So if so we don't have a long-term, basically we can say we don't have an error correction model where our statistical model brings the values back to the equilibrium. But we still have XT predicting or correcting for fluctuations in YT. So we can say that XT is weakly exogenous. But what if this term as well is statistically insignificant? Then we can say that XT can only be explained by its own past values. YT does not explain XT, but XT explains YT. That tells us something very intuitive. It tells us that XT is a part of the equation for YT, which means XT causes YT. But YT is not a part of the equation for XT. All of these terms, which include YT, are statistically insignificant. So YT does not cause XT. So here we can interpret based on causalities. If we have this sort of a relation, then we can say that we have unidirectional causality. Causality goes from XT to YT, but not the other way around. I mean, thinking about the umbrella cells or rain, for example, we can only have unidirectional causality because rain is not dependent on sales of umbrellas, but sales of umbrellas are dependent on rain. Next, we have if both of these error correcting terms for both XT and YT are insignificant, which means that they're statistically not different from 0, then what we have over here is that we don't have any co-integration, we don't have an error correction model, and if we take these out of the equation, then we have a vector autoregressive model, which means that it's very simple to what we studied last time for the autoregressive models, but instead of a univariate model which depends on its own past values, we have a vector of autoregressive models where the values for different variables not only depend on their own past values, but also they depend on the past values of other variables in the system of the equation. So that is a vector autoregressive model. It's a short-term model because we are only modeling the short-term fluctuations in the dependent variable. And if we regress the equation in their level, so without taking the difference, then we can get a spurious regression. But when we try to model it in first differences, our interpretation would be for a short-term model when there is no cointegration. So when we don't have cointegration, we can still go ahead with our analysis, but we cannot interpret the results of this regression as we don't have a long-term relation, because if we do interpret our results based on this regression, we would have spurious regressions, a possibility of having spurious regressions because of no correlations, but we can still estimate a short-term model using vector autoregressive models. So it's the same equation pretty much as the previous one, which is explained by deviations or fluctuations in y can be explained by fluctuations in previous values, previous fluctuations in y and previous fluctuations in x. And in the very same way, fluctuations in x can be explained by previous fluctuations in itself and previous fluctuations in y. So this over here would be an example of a vector autoregressive model. Moving on, we will look at how we can examine multivariate time series using a demonstration of per capita consumption and income. And I've gathered data from the Office for National Statistics of the UK. And I'll show you how the data looks like, and we will see if it's cointegrated or not. If it's cointegrated, then we can go for the vector error correction model. If it's not cointegrated, then we would have a vector autoregressive model. This is how the data is structured. It's quarterly data from 1955 up until 2020. And the data is for per capita consumption and per capita income. The idea being that people adjust their consumption depending on how much they earn, but do people also adjust their income depending on how much they want to consume? At the end of the day, people consume what they earn. This is the disposable income. So after deducting for taxes, people consume what they earn, which is why we have, when we plot it, people, we have these values pretty much very close to each other. But are these co-integrated, or is it going to be a spurious regression? If they are co-integrated, then we can have a vector error correction model. So, I mean, most statistical packages can do that. I will just use data for demonstration. We are going to import this data set. Consumption and income, import first row as variable names. As always, we have one problem over here. The variable Q, which stands for quarters, is not identified by Stata. So Stata is looking at this variable as if it was just some random text which Stata does not understand. So whenever that happens, we always have to tell our statistical package what the variable actually means, and it's a variable that explains the time that is being used in our analysis. So we have let's generate another series called T, which is quarterly, and that is basically the same as Q. And we are trying to explain Stata that this is structured as year first, quarter after. And now we have another variable T, and we have to say that for time series, we set this variable T as the time of our analysis for our variables, and this is quarterly. So here we go. So now Stata understands what T actually is, and interestingly, these two variables, although look pretty identical, Stata will not identify what Q is, but Stata would identify what T is because we have explained. So that's just something we have to do every time. All right, let's have a look at how our data can be displayed. We have consumption and income. And by the looks of it, it looks like both of these are non-stationary. So they are not white noise. But just to confirm that, we can quickly conduct a Dickey-Fuller test for consumption. And as expected, we fail to reject the null hypothesis, which means that the data for consumption is non-stationary. But when we do the same analysis for, let's say, the first differences of consumption, which means the periodic fluctuation in consumptions, that would be stationary. Let's look at how that series looks. If we plot the first differences of consumption, then we have something which is pretty much close to a stationary series. So to be sure that this is a stationary series, we can conduct the same Dickey-Fuller test again. But for the difference of consumption, and we reject the null hypothesis this time, saying that consumption is actually a non-stationary series, but when we take the first difference, the series becomes stationary or white noise. Okay, after doing the same for income, which is our second variable, stationary, non-stationary in levels, stationary in first differences, most probably. And here we reject the null hypothesis. So we can, once we have these, we can go ahead with our co-integration tests, because in order to use the Engle-Granger co-integration test, we need to have our data series, which is non-stationary in levels, but stationary in first differences. Okay, so let's do this manually so that we can have a better interpretation of what we are doing. What we'll do now is we will conduct a simple regression where we try to model consumption, and we try to explain consumption by, let's say, by the values of income. And we get this, oh, we need to use regress as a command, all right. Then we get this, where consumption can be predicted by changes in income, and the p-value is pretty strong, which says that we have a very strong statistically significant correlation. But is there an actual association between these variables? In order to examine that, we have to conduct a co-integration test. So in order to conduct the Engle-Granger co-integration test, we have to predict the values of the error term, which means we have to extract the values for the error term. If we were to use these coefficients to compute values for consumption and then find the difference between actual values of consumption and our predicted values of consumption, we would get the error term. So we predict, and let's call this new series of predicted residuals. Residuals is another fancy word for error terms. When we do that, we have another variable, which is u. And when we have a look at how this can be graphed, we have u, which looks which looks stationary. If this is stationary, then we would have co-integration. That's simply what the Engle-Granger co-integration test is. So in order to examine if this is stationary, we conduct another Dickey-Fuller unit root test, but for the values of our predicted residuals. And since this is the error term, which is always supposed to be averaged around 0, we don't have a constant. We get a t-statistic of -4. And Engle-Granger, who came up with this co-integration test, have also explained how these critical values for the Dickey-Fuller test would not be reliable, because we are comparing our t-statistic for a decoupleur test of a variable which is already estimated. So when you estimate this, you already have a chance of this not being you already have you're already relying on a level of statistical significance for this, and then you are conducting a unit root test on a variable that is predicted. So we would compare these against another set of critical values, which if you Google or find out Engle-Granger co-integration test critical values, you'll find out. And what we will get is that this statistic actually crosses that critical value as well, that 5% critical value, which doing so explains that this series is stationary. Hence, we have co-integration between income and consumption. Since we have co-integration between income and consumption, we can regress. We can regress the same consumption on income, and we can also introduce the lagged value of our error term, which will be our error correcting component in the model. So when we introduce the lagged value of our error term, we have to regress these in first differences for the error correction model. Because there is co-integration, we can also form statistical inferences based on our original regression model as well, which is this one. And the results from these are reliable because we have co-integration. But we can also go ahead and form an error correction model as well, like this one. This one's a simple error correction model where we have introduced one lag one lag of consumption, one lag of income, and we can also introduce, when we regress consumption, we can introduce the lag of itself as well. Basically, the idea is that what I want to explain in this part of the vector correction model is that this is negative and is the error correction term. So that can be seen as the speed of adjustment, 0.17. It's between 0 and 1. What happens is that if there is an error in consumption and consumption is below the equilibrium, then that is captured in the error term. But the error correcting term will bring consumption back towards the equilibrium at this speed, at the speed of 17% per se. So we can model using the error correction model, which tells us that we have a strong long-term association between consumption and income. And that's a very simple example. Theoretically, we would expect these two terms to be correlated as well. But I've specifically used this today for a simple demonstration. You can introduce more lags in your error correction model. Depending on the way your data is structured, certain number of lags might be better. Right, we'll get back to our presentation now. So what we have done today here is a summary. When we have multivariate time series, we conduct unit root tests to measure stationarity. We explained what unit root tests were in the last session, and we have used these unit root tests to find out if the series are stationary. If our original series are non-stationary, then we can just go ahead and construct vector autoregressive models or go ahead with Granger causality tests. If these series are stationary, if these series are integrated at the same order, which means that not stationary at level, stationary at first differences, we can go ahead with co-integration tests. We could use Engle-Granger or Johansen co-integration test for this. If we do not have co-integration, then we use vector autoregressive models. If we have co-integration, then we can use vector error correction models. After both of these, we can still go ahead and look at Granger causality test, because from the vector autoregressive models and vector error correction models, we cannot directly, although we can kind of from the vector autoregressive model sense if there is causality. Going forward and conducting a Granger causality test can tell us more about our data series. And Granger causality test would explain that not only these variables are associated, but this is the direction of their, which tells us that maybe what if we have a situation where people decide how much they want to consume based on their income, but they do not decide on how much they earn based on their consumption. So theoretically, if this makes sense, we can go and test that with a Granger causality test. And that would be the last thing which we would do for today's session. A Granger causality test looks pretty similar to a VAR model. Conceptually, the idea is pretty simple. The idea is that when we are trying to model fluctuations in a particular variable, let's say we have a particular variable, let's say consumption or income, and we are regressing that on the past values of itself and the past values of another variable, or one or more other variables. We can have a longer equation, not only include consumption, but savings and income and so on. But the idea is simple, that since we are including only lags, if we have an association, then assuming that time travel is not possible, which is the kind of assumption that makes it more interesting. If time travel is not possible, then if two variables are strongly associated with each other, then only what happened first can affect what happened next, and not the other way around. So something that happened in the future simply cannot affect what happened in the past, but it's only possible that what happened in the past, because these are lagged values, past values for the variable itself and for another variable. If we have a situation where past values, past fluctuations of xt can be used to explain present fluctuations in yt, then we have causation. And that's the theme of Granger causality test. It's very simple to understand. If we have past fluctuations in xt, and we're not looking at current fluctuations in xt. So for past fluctuations in xt, if they're found strongly associated with yt, then we can only have, once again, assuming time travel is not possible, we can only have past values of xt that can predict current fluctuations in yt, and not the other way around. If there's a fluctuation in yt, yt cannot go back into the past and make changes or affect xt that has already occurred in the past. And similarly, we have a vector of this. So we are also looking at if we have causality the other way around. So current values of xt are modeled against past values of yt and past values of xt. So if we have a situation where xt can be predicted by past values of yt, with, let's say, consumption, today's consumption can be predicted by what income was yesterday, then today's consumption it's simply impossible for today's consumption to go back in past and affect what our income was yesterday, but it's only possible for our income yesterday to affect today's consumption, if that makes sense. So when we model that idea, we use Granger causality test equations, and we have the theta values here, which are for the, and we are just looking at the statistical significance. And the assumption over here is that if there is no causality, then today's consumption, if there is no causality, if income is not affecting consumption, then yesterday's fluctuations in income are not supposed to affect today's consumption. But if income does cause, if income does Granger cause, that's the term used, if income does Granger cause consumption, then yesterday's fluctuations in income will cause today's consumption to fluctuate. after conducting these hypothesis tests, which with the null hypothesis assume that all of these coefficients are zero for all of the lags of the other variable. If that is the case, then under the null hypothesis, there is no Granger causality. But if these are not equal to zero and therefore are statistically significant, we do have Granger causality, and we can do that with a lot of different multivariate time series to find out more about how not only are they correlated, but how we have causality. And we can have no causality, we can have unidirectional causality, which could go from X to Y or from Y to X, but not the other way around. And sometimes we can also have bidirectional causality between two variables where they are both affecting each other simultaneously. And with that, I'll finish today's session and we'll open the virtual floor for questions and discussion.